Thank you, Greg. And thank you, everybody, for coming here today. And so this work is done in collaboration with Greg Foles from AOML and Karthik Balaguru from the Pacific Northwest National Laboratory. So first, first, as you know that when tropical cyclone travels, it leaves it usually leave back trails, cold trails along with its track, and so this is because of the mixing done by the hurricane wind, and bring up deep, cold, nutrient-rich water from subsurface to surface, and creating the cold wake here. And also, this also lead to increasing in primary production, as we can see that Hurricane Katia in 2011, it leaves very high chlorophyll trails along with it. And another local effects of TC-induced mixing is through heat. Emmanuel was the one who first proposed this, so the red here we show the red profiles is the pre-storm temperature profile, and the blue one is the post-storm temperature profiles. And so the red one is pre-storm, the mixed layer is shallow and the temperature is higher. And after mixing, the mixed layer becomes deeper and the temperature is cooler. And so the total heat amount from the surface, the rectangle area here is pumped down to the diagonal area. And so this is the results from Chang 2016. And he showed here a composite, the difference of composite map, Hofmüller plot of pre-storm versus post-storm temperature profiles. So this is the depth, and this is the time. And they did this for the Northwest Pacific, and we can see from here that on the surface we see a cooling of temperature, and beneath it we see a warming of subsurface temperature. And most of the warming happens in the upper 100 meters, and it can reach to 200 meters. So that is the local effects of tropical induced mixing. So how about the global effects? So here we show a map of cumulative wind intensity of tropical cyclone, annual cumulative and average over the period 1982 to 2018. And the storm track data is from IB tracks. And below here, we show the cold wake computed over the same period using optimal interpolation SST, OISST. And we can see that there is the co-location of the intense storm center with the intense cold wake from here. And so the first possible effect proposed by Chang 2016. So they did their study over the Northwestern Pacific, and they found that they found a decreasing trend in SST cooling, or increasing trend in the cold wake over this area. And this here in this plot, they show the pre-storm sea surface temperature. There is an increasing trend from 1980s to 2015. And so they proposed that because of this increasing trend in cold wave, it has there is an offset in SST warming, meaning that without the cold wave, the SST warming would have been higher. And so from here we have a question, like, so there's a cold wave trend over the northwestern Pacific. So how about at global scale? And in their study, they explain the cold wave trend by showing an increasing trend in the total time of wind at different categories. However, they didn't mention the other possibilities, for example, translation speed or ocean stratification. As you know, translation speed can also impact the cold wave. If a TC moves slower, that means it can induce more mixing, and so the cold wave can be stronger. Or for over very stratified ocean temperature stratification, the thermocline would be very close to the surface, and so a given TC can produce more cooling for that. And so in this study, we will also address all of these possibilities. And and so in their studies, they show there is the increasing in the cold wave, but we also see that there is the warm, that there is more heat and more heat pumped to the subsurface layer. So maybe, and after that, you know, after the cold wave is formed, maybe it takes a month so that the surface, the mid-layer temperature can be restored to its climatological condition. However, the heat that was pumped down will remain there. So maybe it will have some role or have some contribution to the global warming trend. And so the second global effects that it may have, as suggested by Nguyen in 2001, is that if the TC-induced heat pump will, the heat pump down will ultimately be transported forward, and he found that this amount of heat pump can reach about 1 petawatt, and based on a couple model for the year 1996. And following this study of Nguyen, Shriver, and Huber in 2007, they proposed that TC-induced heat pump can contribute up to 15% of big marine heat transport using realized this data. And however, the validity of the assumption that all of the heat pumped down by tropical cyclone will be transported forward is still questionable. First, it would take a long time to remove the excessive heat induced in the main development region. Because, for example, if we look at the northern Pacific, and let's take a simple math calculation. So the tropical North Pacific extends from 120 east to 120 west. So that makes 180 degrees, and from 0 to 30 degrees north. And for the upper 200 meters, so the crucial currents, the fastest westernmost currents, then with mean annual transport of about 30 square. So it would take about 11 years for the crucial to drain out the tropical North Pacific water. And there is also the recirculation of other current like the California currents. And so this recirculation would extend the time scale of for the heat to be totally transferred to the pole. And a second point, as pointed out by Johnson in 2010, is that winter mixing, when winter mixing can deeper the mixed layer, and then so we will reabsorb some of the excessive heat and then release back to the atmosphere. So that's and the third possible global impacts is that is on primary production, and here we show the cold wake map as seen before, and this is the chlorophyll OCCI chlorophyll computed using the same over the same period, and we can see that there are center of high chlorophyll that coincide with center of strong cold wake here, and just to give some idea, so a single typhoon can induce about 0.8 million tons of new carbon fixation, and TC-induced primary production can contribute up to 20 to 30% of annual primary production in some region with high TC activities. So another question is that, so if there is a cold wake trend, would the cold wake trend lead to a primary production trend? And so this consists of the objectives of our studies. So first, we want to figure out, we want to find out if there is a cold wake trend at global scale, and then what causes the trend, and then what are the implications on global warming or primary production. So let's go through this one by one. So to find the to find out if there is a cold wake trend at global scale, we use IB-TRACS data, and we use SST satellite SST data, OISST, which is available since 1982. And we also use microwave SST data to intervalidate with OISST data. And the method is simple. We adopt the method from Chang in 2016. So the SST-cooling is the SST of post TC minus SST of the pre-storm. So we only take into account those TC with from tropical storm up to category 5, because tropical depression is too weak to create any to induce any significant cold wake. And so we at each location we compute average of a 4x4 degree beam, and the pre-TC time is 2 to 4 days before TC, and the post-TC time here is 1 day after TC. And so after we will also test on the sensitivity of this choice later. So this is the result. This is for the trend of OI, the blue line, microwave SST, the red line, for global, for Northern Hemisphere, and for Southern Hemisphere. And first we can see that there is significant trend with highly significant trend in both hemisphere and at global scale. And we can also see that for microwave is also show a decreasing trend in SST-cooling. Here consistent with OISST, but with much stronger magnitude. So OISST has the limitation due to cloud, whereas microwave SST doesn't have this limitation, so show stronger magnitude of cold wake. However, they both have a very high correlation, the detrended correlation between them from 0.6 to 0.77. So that means that they are in highly agreement. And this is the results for smaller development basin for North Atlantic to South Pacific. And most basins have very significant trends, more than 90%, except for the North Indian Ocean, because for this basin, the data is limited down to 1990s. This is not because of the SST limitation in SST data. It's because of the limitation in storm track data. In IB tracks, we couldn't find storm track data before this period for the North Indian. And so we have seen that the trends are very highly significant. Now we do some sensitivity on the choice that we the average, the area average, and on the time average to compute the SST cooling index. So, for instance, here we see that we tested with different beam size, 2x2, 4x4, 6x6, and generally, as the beam size increase, we see a decreasing in trends, similarly in the northern and southern hemisphere. But the p-value of remains highly significant. And we also tested with different averaging periods, pre-storm 2 to 4 days, mid-storm 2 to 12 days, post-storm 1 day, post-storm 1 to 5 days. And the significance level doesn't change. Only the southern hemisphere express slightly change in p-value, but still the p-value is still very highly significant. As we know that SST, sea surface temperature, is closely connected to ENSO and also the cold wake. And so we want to remove the ENSO activity, the ENSO signal in the cold wake to see if it still remains significant or not. So to do that, we first compute a correlation between ONI index and the cold wake index. And from here, and we compute with different lag of ONI from two years to positive 1 year, and for month from 1 to 12. And we find that this blue number represents the period of high correlation between ONI and the cold wake. And so we average the ONI index over this high correlation period. And then we do regression in order to remove the ENSO effect. And then we can compute the trend on the residual signal. And here's the results. Here we show the original trend and p-value. And here's the trends and p-value after ENSO is removed. So the p-values remains the same. So that means the significance doesn't change. So ENSO doesn't have any effect on the cold wake chance. So just to summarize, so we found a consistent decreasing trends of cold wake at global scale in both OI and microwave SST. And the global trend significance is insensitive to area time average and to ENSO effect. So the next question is that what caused the trend? So as we know that 3 different factors that can affect the cold wake magnitude. So Vmax, so for increasing in the cold wake magnitude, Vmax needs to increase or V chance needs to decrease, or the temperature gradient needs to increase. But if we look at this, Vmax doesn't show a significant trend. V chance show increasing trend. That means it's getting faster. So this cannot explain for the cold wake trend. And also the temperature gradient is decreasing. So it cannot explain for the increasing trend of the cold wake. But if we limit to the category, to those tropical cyclone with intensity from category 1 to 5, which consists of about 36% of total data, we can see that the translation speed and temperature stratification still have the same behavior, but the Vmax increase with a significant trend. So this is the only reason that can explain the increasing trend in the cold wake. And so next, where are the trends? So because we don't have enough data to compute the trend at every single location, so what we do here is that we take 2 different decades, the first decade and the last decades. We compute the mean cooling of the decade for every 5 by 5 degree beam. And here's the map, resulting map for the first decade, and here's the resulting map for the last decade. And here's the difference between the 2 decades. So we also do the same for Vmax, for the maximum sustained wind speed. And here we show the SST-cooling difference, decadal difference, and Vmax difference, decadal difference. And so we see that there's a consistent and strongest difference in the Southwest Indian Ocean, where we have stronger cold wake here and stronger Vmax here. And in some other smaller region, there is also this consistency. And if we limit to only Cat 1 to 5, the map of the cold wake exhibit a bluish color. So the blue color dominates the cold wake. That means the later decades, the cold wake is stronger than the first decade. And also in the Vmax map, the reddish color dominates the blue. So that means, and they are very, consistent between Vmax and cold wake. And so it means that this is happening everywhere globally. That's ultimately contribute to the global trend of the cold wake. So next, what is the implication on the? So we see increasing in trend in the cold wake. So how it contributes to the warming trend of the tropical ocean. And so our assumption is if you so before the study of China, they propose that the TC activities lead to an offset in SST cooling. And so that is about the surface layer. So now we see the heat is pumped down. So our similar question is that, can this heat, pump down heat can also contribute to the warming trend of the ocean heat content for the first 100 meter or for the 200 meter layers? And to find this out, we at every location we compute the heat-induced, the depth integration of the heat-induced tropical cyclone-induced heat pumping by computing this area from the top layer, and with simple geometry we can solve for the area of this upper layer, because the assumption is that the amount of heat in this upper ocean will will be pumped down to this triangle. And so after that, we do the track integration along the track. So we integrate the mean ocean heat content with depth, we multiply it by track length and track width to have the TC-induced ocean heat pump for the track, and then we integrate all of the tracks in the year to get the annual index for TC ocean heat content. And so in order to compute this, there are two factors, there are two parameters, that is the isothermal layer depth and the temperature gradient that we need from the ocean. And in this study, we obtained them from four different ocean releases: EN4, Godas, Oras4, and Soda. And so because looking at this map, the Northern Hemisphere, there are more TC activities, whereas in the Southern Hemisphere, there's less activities and there's no activities in the Southern Atlantic and in the Southeastern Pacific. So it will be more meaningful to compare the TC-induced heat pumping with the tropical ocean heat content for the Northern Hemisphere. So we can compare this by integrating all of the heat induced by TC from 0 to 30 degrees, and then we divide this total heat induced by the total area of the tropical ocean to get the mean value in joules by meter square induced by the tropical cyclone. And then we can compare with the mean tropical ocean heat content for the first 100 meters, where most of the warming happened, or over the first 200 meters, the maximum depth of TC impact. And here's the result. So this is for 100 meters, and this is for 200 meters. And I want to, so the green lines show the TC-induced ocean heat pump, and the purple line show the ocean heat content over the same area. So this is from EN4. And I want to highlight that the ocean heat content magnitude here is 10 to the 10, which is 3 orders of magnitudes larger than the TC-induced ocean heat content year to year. But if we look at the trend here, the trend in the ocean heat content is only 1 order of magnitude larger than the TC-induced heat pump. So to the 6, and here is to the 5. And so this shows the relative contribution of the TC-induced heat pump for the upper 100 meters in the Northern Hemisphere, Northern Tropical Hemisphere. So for EN4, it ranges from 4.5 to 10.4% for the upper 100 meters, and it's from 3 to 7% for the upper 200 meters. And and if we look at this, we can also see like there's periods that the ocean heat content is closely related to ANSO. So we also want to remove the ANSO effect to see whether the contribution, how the contribution, relative contribution will change. And so this is the effect when ANSO is removed. So red means increasing and blue means decreasing. So for the upper 100 meters, it's slightly increased the contribution, but it's slightly decreased the contribution of TC-OSC for the upper 200 meter. And finally, what is the, is there any trend on the primary production? So here we see here we see that we find that there are increasing trend in global of cloud. So the green line here is the SST cooling, and the purple line here is the chlorophyll concentration. And so we found increasing trend of chlorophyll and decreasing trend of cold wave as expected. But the increasing trend in the at global scale or the northern hemisphere, they are not significant. And if we change, so here we do over 4x4 beam size, and the same as the same way that we did with the cold wave. And if we change to 2x2 degree beam size, and if we look at this, we exclude the coastal areas where we have very strong chlorophyll as well as sometimes negative TC-induced chlorophyll A. So we exclude those locations that is close to the coast. And we found that the trend in the southern hemisphere becomes significant at 99%. So, but the global scale and for the northern hemisphere, it's still not significant. So this means that chlorophyll trends very sensitive to area, time average, and to distance to land, whereas the SST cooling always stay very always highly significant. So we're still working on this to figure out the reason behind this sensitivity of chlorophyll A. But the possible reasons could be, first is due to the difference in thermocline and nutricline depth, or is the possible impacts of coastal water and data uncertainties for chlorophyll A maybe is much worse than the uncertainties from satellite SST. And so to conclude, so we found a significant trend of TC-induced SST cooling. So this is an evidence of increasing mixing of TC due to a stronger intensity of those who are in category 1 to 5. And the associated TC-induced heat pump can contribute about 10% to the warming trend of the upper 100 meter and 5% for the 200 meter layer in the northern hemisphere. And there are increasing trends in primary productions, but the trends are sensitive to time area average and distance to land. And yeah, then so thank you for your attention. And if you have any questions, please let me know. So I got a comment from Sima Berson about JTWC has best track data for the Indian Ocean starting from 1945. So what I found in IB tracks is that the the data for Vmax is all of them are missing values from 1990 to 1980s. So I will look back. I will look into this information. Thank you, Sim. How did you filter answer from your time series? So Marlos asked how to filter answer from time series. So I did regression, just simple regression, and then from there we can take out the signal from creating from answer. Just do simple regression and remove the signal associated with answer, and then we can compute the trend from the residual signal. Hyun Suk Kim asked a question: are these statistics found for each season of for the entire year? This is for the entire year. Who is this? Dongmin asked, is there any other factors to affect primary production trend, which is not exactly matched to SST cooling trend, such as TC-induced precipitation? This is also another possibilities that lead to this. So yeah, we're still working on this to really figure out why there is this difference between cold wet trend and why there is the sensitivity of chlorophyll trends to so many factors. That could be a good reason for that. Thanks, Dongmin, for the comment. Yeah, so the presentation I think will be available online, I guess, at AOML. Your identity is so Hyun Suk Kim say that your identity SST is based on mixing, and chlorophyll change is driven by storm-induced upwelling. Delta SST is based on mixing during the storm-induced upwelling. I expect you may not get good and clean relationship unless you consider advection. Yes, so upwelling is, upwelling may also bring cold water to the surface, right? So but the chlorophyll would definitely take some time to build, and so the time averaging may be also very important. So we're still working on this. So is there anyone who wants to ask directly on this?